Okay, welcome back. So we have already done number theory problems almost over a week. So today let's take a break from number theory problems and we're going to do calculus problems. So remember from videos from last week and 2 weeks ago, I've actually done a video that is about the first derivative of x to the x power and also x to the x power. And in the short video, we were using the what's so-called trick to get the derivative quickly by saying that we have to treat the two parts as two different functions, and then we'll just use the product, somehow kind of like a product rule to do it. So in the video, we said that we could just get something such as, first, we're going to look at the red part as our function, where the blue part right now is temporary some non-x function. So in this case, we will just have some function raised to some tree as constant power. Then if we take that derivative, we will get f of x raised to g of x power, of course, minus 1 by the derivative of power function. Well, of course, in this case, we still need to do a chain rule because we don't have x as our base. We have f of x, so we need to multiply with the first derivative of f of x, which is f prime of x. Great. And then next, we're going to treat the blue part, g of x, as our function, where f of x is now temporary, not the x function that we're thinking of. So we now have some technically constant base raised to some power in functions. So we will then get f of x as the base raised to g of x power. Then we're going to multiply with ln of the base. Just like when you have a to x power, if we take the derivative, we get the thing itself back, and then multiply with ln of the base. And again, the e case is special because if we put it as ln e is equal to 1, and that's why we can ignore it when the base is equal to the natural number. Anyway, we now get ln of f of x. But don't forget, we're not done yet, because now we're raising to g of x power instead of just x power. So we also need to multiply with the first derivative of the exponent to complete our expression. Good. So we just said that, and this is how we did what's called a shortcut for some problems such as x to the x power or x to the x power. But why is it true? Why are we actually allowed to do this? So in today's video, we're going to verify this expression. Okay, meaning that suppose we don't know, we can use this method by covering and treat one part as a function and the other part as constant temporarily. How can we actually get this result back? So this is what we're going to do. Here we go. First, suppose we don't know, we can actually cover one side and then figure out the other side. If we have to take the derivative, of course, since we don't have a constant base yet, let's raise it to a constant base, meaning that we're going to take e as our base. Then now f of x is going to be part of the exponent, and it's going to become ln of f of x by the definition. And don't forget, we still need to raise the whole part to the g of x power. So if we rewrite it, we would just get the first derivative of e raised to the g of x times ln of x exponent, like this. Cool. So now we have a constant base, and in fact, we just have base e here raised to just some product of functions, meaning we can now take the first derivative, and we are going to use the result. We know that if we have e to some power, if we take the first derivative, we will get e to the same power back. So we get e to the g of x times ln of f of x power times. And now, since we don't have x as our exponent, of course we need to use the chain rule to take the first derivative of the whole exponent, meaning we are going to take the derivative of g of x times ln of f of x. Great. So let's figure it out. We get the first part is still the same, times the derivative of a product. So of course, we gotta use the product rule. So by the product rule, we're going to take the derivative of the first part, which is g of x, times the second part, ln of f of x, plus the first part, g of x, times the derivative of the second part, which is, in this case, remember, the derivative of ln of something is just the thing inside of the natural log, which is, in this case, f of x. But since we don't simply have x inside, we have to use the chain rule one more time. So we need to take the derivative of f of x, giving us f prime of x. And that is what we get. So let's try to wrap up and rewrite some of the expressions to see if we can actually get the same results back. So first, the first part, e raised to some power, we can just rewrite back as f of x raised to g of x power. Great. Now for the second part, we get g prime of x times ln of x plus, here I'm going to put the numerator together. Actually, I'm going to write this way. We will have g of x times the numerator f prime of x times the denominator. So this is the same as saying we are raising the f of x power to the negative first power. What? The f of x function to the negative first power. Good. So if we multiply this back into here, and I'm going to write the second part first, we will then get f of x raised to the g of x power. And then here we have another copy of f of x, but raised to the negative first power. So we can combine the exponents together by the addition rule. We get, well, actually they call it product rule, I don't know why, minus the first power, okay? And then of course we just need to multiply by the remaining part, g of x times f prime of x. Good. And now we just need to copy down the other part, which is plus f of x raised to g of x power times, and I'm going to rearrange the order of the expression again. We get ln of f of x, and then finally we're going to multiply with the g prime of x. And then that is it. And this actually shows that our thought of taking part of the expression and do it separately is actually going to work, because we actually end up with the same result. And again, why? That's because of the property of e raised to some power, and then we can show that no matter which way we look at, we actually get the same thing as we want. Pretty cool, huh? So, yep, that's it. And we just show that now we can always use this trick no matter in what situation. So, in this case, when we have to take the derivative of these kinds of problems again, we don't have to do all the works or get scared away anymore. We can just simply think of the trick that we just used and think of how we actually can chop up the problem into parts and figure out each part individually to get our final answer. So if you enjoyed this video, don't forget to like, and if you want to check out more of my videos, please subscribe and also click that bell and to turn on the notification, and so that you won't miss any of my new videos either. That's it. See you guys next time.